So, hello everybody. For the people who needs the certificate of attendance for reimbursement and so on, are here, okay? You just fill with the name and the title of your talk, of your poster in case, okay? I put them here.
Se può proiettare. Good morning, everybody. Let us start the last session of this great meeting. I thank all the participants and the speakers for the marvelous talks. In particular, I like to thank Professor Hugo da Veiga, who first contacted me to make a celebration for the 65th birthday of Professor Radulescu. I was so happy. Since I am retired, I could not manage in my university. And so Professor Cassani offered us this marvelous opportunity to use this center, the Riemann Center. So I'm very grateful, and the organization, as everybody said, was just magnificent. Let me say that Professor Radulescu is strongly related to the Italian school, not only to the Chinese school, and maybe to the French school much before than the Italian and so forth, because it is, as you know, an international international master in mathematics. And I want just to emphasize the connection he had so strongly thanks to his deep friends of Italy. So he's a member of the Accademia Peloritana dei Pericolanti di Messina since 2016. That this academy was founded in 1729, and a corresponding author of the Accademia delle Scienze dell'Umbria, the Academy of Sciences of Umbria, which is my region since 2017. And as maybe someone could hear yesterday, because it was not so easy to hear, Professor Lino Conti, who is the president of the Academy of Sciences in Umbria, gave for the greatest achievement of Professor Radulescu in mathematics to be honorary member, which is extremely rare for a professor abroad. So I am really grateful because Professor Radulescu visited my department and university since 1999 regularly, and gave his support, his time and everything with great generosity to all the school in Perugia. So everybody of us are particularly happy. So let me show something that first of all, I thank very much Professor Radulescu for the friendship and the continued support he gave me. And I am also very grateful to him, to Professor Radulescu, and the honorary editor of this volume was Professor Serrin. And we wrote this collection, 2 volumes with Professor Radulescu, Professor Weinberger. For me, this was the most exciting mathematical experience in my life. So I'm very grateful. Naturally, Professor Radulescu has several important monographs, but this was really a giant work we did together. This is one of his visits in Perugia in 2016, and here I am in the same year in Craiova, and here is the next year again for this important conference in memory of James Serrin, with so many friends of him and colleagues. And here is the lecture of Professor Radulescu at the conference. Here is in the audience with many friends that you can see. And here, as I said before, Professor Radulescu entered in the Academy of Science in Umbria in 2017. And the first lecture he gave in the Academy was in my department in January 2018. This is the picture of the lecture. And here I want to thank him also for the help he gave me in supporting me in China. And when you have a friend in China, you have a friend forever. As Professor Radulescu is a friend of me forever. And so you see these people in the audience, and so I am particularly grateful to him for this marvelous experience that I had in China, thanks to Professor Radulescu and my Chinese friends. And here is just last year, a few months ago, with our Italian friends, that they gave me a celebration because I was 70. And so I'm very happy because all these friends are here in the audience. And so with all of us, we want to say happy birthday, dearest friend. And your 65 years of living have been a great blessing to your family and friends. And our lives are all enriched because of you. We are wishing you a superb 65th birthday, dearest Vincenzo. Happy birthday to an exceptional friend as you, wishing all the best that we can imagine to you and to your dears for the next 65 years and even more. Daniele, Hugo, and Patrizia. Thank you very much. Let us now start with one of I met Professor Nicolas Papageorgiou in Perugia many years ago. He was in connection with Professor Averna and his school. Professor Papageorgiou will speak about the singular double phase Dirichlet problem, and he is from the National Technical University of Athens. So thank you very much, Professor Papageorgiou, to be with us.
Okay, first of all, I would like to say happy birthday to a distinguished mathematician, exceptional person, and a dear friend. Happy birthday, Vincenzo. And also to Professor Cassani, thank you very much for this remarkable meeting. Okay, so my topic is singular double phase Dirichlet problems. It's a joint work with two colleagues from China, Professor Bai and Professor Zhang. Okay, so the problem is this. Omega is a bounded domain with C2 boundary, and we are dealing with this singular equation. What the hell is that? How do you... Excuse me? There. Ah, okay. Sorry. Okay. So this is the problem that we are dealing with. We have two parameters, mi and lambda, and P and Q are related like that. This is a weighted Laplacian, with the weight being an L infinity function different from 0, but the important thing here is that A may vanish. Okay, and these problems are called either double phase problems or problems with unbalanced growth or PQ problems. They started in the late 80s, early 90s by Marcellini and Zhikov, who produced the first basic results. Here is the weighted Laplacian, and of course if A is equal to 1, then you have the standard P Laplacian. What problems do we face here? It's a singular problem, first of all. So the energy functional of the problem is not C1. So we have to find ways to isolate the singularity, bypass the singularity, and deal with C1 functionals in order to apply the minimax theorems of critical point theory. This is one difficulty that we face. Second, because of the fact that we have a double phase problem, first of all, the standard Sobolev spaces are not enough. We have to move to generalized Orlich spaces. This is not such a big difficulty. But the basic difficulty is that for those problems, we do not have a global regularity theory. And for example, there is one result that is very useful when dealing with balanced growth problems that goes back to Brezis-Nirenberg and says that if you have a C1 functional and a local minimizer for the C1 topology, then this is also local minimizer for the Sobolev space. This, if you look the proof of that result, is just the Lagrange multiplier rule and then the regularity theory of Lieberman. If you do not have regularity theory, global regularity theory, regularity up to the boundary, you cannot use that result, and we will see in the process of the proof where we have difficulties exactly because of this fact. Okay. Here is the density, the double phase density. You see, this is the function eta, which is az times t to the p plus t to the q. I apologize because for me p is the bigger index, not the opposite. The reason is usually we were studying p Laplacian problems. So when we pass to double phase problems, I want the dominant exponent to be the p, not the q. For that reason, I have p bigger than q. Okay, and you see that this double phase density has different growth from below and above. Q from below, P from above. This is the source of difficulties. Okay, now, as I said, we will use generalized Orlich spaces. Here are the assumptions for the A. The A coefficient is Lipschitz up to the boundary, non-zero, positive, non-negative rather, and we have this condition here, and also this which is standard in double phase problems. And finally, I have a restriction on eta. We will see why I need that restriction in the process. The assumption that it is Lipschitz, this coefficient, means first of all that the Poincaré inequality is valid in the generalized Orlich space. And since we will use the Dirichlet generalized Orlich space, we can work with a norm that corresponds to the gradient. Okay, and also this condition here implies that P is less than Q star, which in turn implies useful compactness embeddings. Okay, so let me give you a quick review of generalized Orlich spaces. First of all, let's call lambda 0 to be the space of all measurable functions. Then this Orlich space, generalization of the Lebesgue space, is all measurable functions for which this function here is finite, this integral. This integral here is called modular function. It's easy to see that it is convex continuous. Therefore, by Mazur's theorem, it will be weakly lower semi-continuous. We can equip this with a so-called Luxemburg norm, which is given here. Because the function eta is uniformly convex, this space here is uniformly convex, separable, and being uniformly convex, by Millman's-Petit's theorem, it is reflexive. Okay, then having this space here, you can define the corresponding Sobolev space by requiring that U belongs in the space and the absolute value, the norm of du, to be also there. Okay, and then, of course, you give it this norm here. Okay, we can, but for us, because of the Dirichlet boundary condition, this is the interesting space, which is produced by taking the test functions, continuous functions, infinitely many times of compact support, and close it to this norm, this Sobolev norm. Okay. Then on this space, as I said, the Poincaré inequality holds. Namely, we have this inequality here with C being independent of U, and therefore on this space right here we can use this norm. Okay, as it is in the classical Sobolev spaces. Now, first result is that there is a close relation between the modular function and the norm. Okay, and here is the relation in this proposition. This first condition here is called the unit ball property. From this, you can derive easily the other properties, and you see if I can estimate something using the modular function, I can estimate also using the norm, and vice versa. Okay. Second, we have nice compactness results, compact embedding results, like the Sobolev embedding theorem. Okay, here are the embeddings continuously. This is the Sobolev embedding theorem. You see here is Q star, the smaller exponent, and compactly if we have strict inequality here. We will need all those facts. Now I introduce the double phase operator, which is this operator. This operator is bounded, maps bounded sets to bounded sets. It's continuous, strictly monotone, therefore maximal monotone, and this is important because maximal monotone operators have very nice surjectivity properties, and surjectivity properties imply existence theorems. And it has the S plus property, which is this property here, which is the appropriate tool to check the Palais-Mail condition. Okay, we will use this notation here, another modular function, for this part of the original modular function. And this function too is continuous convex, hence weakly lower semi-continuous. Now, I will use this notation here to mean that for every compact subset of omega, this function is bounded away from 0, almost everywhere. This means, therefore, that this function is almost everywhere strictly positive. Okay, I will use this notation for this order interval, and then we come to this space here. If we were in the balanced growth setting, this would have been very important space, because by regularity the solutions would have been in that space. Now we will use it, but it will not be the central space in our considerations. This is an ordered Banach space with positive cone, this one, and this cone has a non-empty interior given by this expression, this being the normal derivative on the boundary. Okay, now some of the mathematical tools that I will use. First of all, some notation this is the critical set of the functional phi, which is a C1 functional on a Banach space X. Given a topological pair like this one, we call HK Y1, Y2 to be the kth relative singular homology group. I'm going to use critical groups in order to produce extra solutions and distinguish between solutions. What is this critical groups? It's an object that we take from algebraic topology. How do we define them? Okay, let U be an isolated critical point and C being the critical value. Okay, we consider the lower level set at the height C. Then the critical groups of phi at U are those homological groups where U is an isolating neighborhood, because you see I took U to be isolated. Okay, this definition is independent of U because of the excision property of singular homology. Also, suppose if we want to have a global theory, suppose that we have a C1 function again that satisfies the ceramic condition, the C condition. I will speak about this in a moment. And suppose that you have a finite set of critical points, and therefore this is less than, bigger than minus infinity. Consider a level below this set. Okay, below, in other words, this quantity here. The critical groups at infinity are those groups here. This, in the first sight, it looks like a not well-defined quantity because it depends on C. Okay. So are we sure that we get the same thing if I change C to a different one? Here comes the properties of homological groups. What do we have here? If you have two values, A and B, two levels, okay, below that value there, this value here, okay, then the level set, the sublevel set at B contains the sublevel set at A. And what happens is that this smaller sublevel set is a strong deformation retract of the bigger. Strong deformation retract means that you have a deformation that brings this set to this set, leaving in the whole process at every time the smaller set untouched. Okay, because if you have two such deformation retracts, one of the other, then you do not change the critical groups, the homological groups, and therefore the critical groups. This therefore shows that the definition is okay. And now, because I don't have the regularity theory, I have to use other tools, and I have to introduce extra assumptions on the functions. And these assumptions are local Lipschitzness. Here I remind you of the definition of the local Lipschitz. Because we are in a finite dimensional space, I use this definition here that the function is Lipschitz at every compact set is equivalent to the standard definition that says every point has a neighborhood where the function is Lipschitz continuous. Okay, and since the functions that we will deal with have two variables, we introduce the notion of L infinity locally Lipschitz. In other words, it's a locally Lipschitz function where this Lipschitz constant is an L infinity function, okay, as a function of the other variable. Okay, here are now the assumptions. Okay, we have a locally Lipschitz integral which has subcritical growth. It is superlinear, does not necessarily satisfy the Ambrosetti-Rabinovich condition. Instead, we have this more general condition here that allows functions with slower increase to infinity than superlinear in the Ambrosetti-Rabinowitz sense. And also we require to be strictly positive and this monotonicity condition here, which is more or less always satisfied. Okay. Of course, since here is important that the function is positive, the F perturbation. Okay, and I will explain later how this is useful. First of all, the two assumptions, the second and the third, imply superlinearity of the perturbation term. Okay, but without the Ambrosetti-Rabinowitz condition. For example, such a function satisfies our assumptions but does not satisfy the Ambrosetti-Rabinowitz condition. Okay, now, as I said in the beginning of the talk, you have a problem where the energy functional is not C1. So you have somehow to bypass the singularity. Since the perturbation is positive, one way to do that is to consider first the purely singular problem. Okay, so we consider this problem here, and we can show, and here is that enters this variable, me, this parameter me. If this parameter is large, then this problem admits a unique solution which has these properties here. Very quickly, let me tell you the proof of that. The proof starts in a standard way that goes back to Crandall, Rabinowitz, Tartar in 1977. What we do is regularize the problem. Okay, we consider this problem here, and eventually you will send epsilon to 0. Okay, and to solve now this problem, we replace u by the absolute value of an LP function. Then we have a problem where the right-hand side is independent of the unknown function. It's an L-infinity function. The left-hand side is a maximal monotone coercive operator, therefore surjective, and therefore this problem with u replaced by the absolute value of an LP function has a solution which, due to the strict monotonicity, is unique. Then I show that, so I have a solution like that. I show that this family of solutions is decreasing with epsilon. This is very easy to see because the epsilon solution is an upper solution for the epsilon prime problem. So as soon as you have an upper solution, you truncate at that point, you apply Weierstrass-Tonelli theorem, and you have a solution. Okay, so we can show this monotonicity condition, and then we are ready to send epsilon to 0. Okay, now, of course, with n, the sequence is increasing. Okay, so we can show that this is increasing and bounded, and therefore it converges weakly in the Sobolev space, strongly in this space due to the embedding theorem. Okay, what I want now, though, in order to be able to use those solutions, is to bound from below by a nice function. So far, the function with which I can bound it is u star 1, which is just L infinity and bigger than 0. This is not good to apply, for example, the Hardy inequality. For that reason, I introduce the distance function, the distance from the boundary. It's a well-known result. You can find it in Gilbert-Trutinger, the book, that because our boundary is C2, there exists a small region around the boundary where this function is C2. Okay, this is the region here. And then I introduce this function here, based on that delta that I have chosen here. This function now is in the interior of this cone. Okay. And for me large, I have this inequality, which means that for my approximate purely singular problem, I have a lower solution. The moment you have a lower solution, you have a lower bound. Okay, here it is. C epsilon being, sigma epsilon being sigma plus epsilon. You send epsilon to 0 and you have this condition here. But as I said, C is in the interior of the cone. Therefore, I have this inequality here. Because C sigma is an order unit, as we say in ordered Banach space theory. Okay, and therefore I have this also. Using Hardy's inequality, you can show that this is bounded, therefore uniformly integrable. It converges point-wise almost everywhere, and therefore by Vitali's theorem I have this, from which I get this condition here, and then the S plus property gives me this convergence, which says that this limit is a solution of the purely bound singular problem. Okay. Now, I had some other properties also. Remember, we have this. Okay, therefore, our solution is, as we claimed, positive in this sense. But also, this is less than this. So I have this. And then, by taking minus eta power, I have this here. Now, about this function, using flattening of the boundary and partition of unity, as it was done in the paper by Laser McKenna in Proceedings of the American Mathematical Society in 1991, you can show that I have this. Okay. And so we have this solution here with all those nice properties, especially this property here is good because of this condition here, which using the Hardy inequality gives us good results. So we have solved now in a unique way the purely singular problem. And now we introduce the two sets that are important to us, the admissible parameters and the positive solutions. Okay, first of all, we show that the admissible parameters is a non-empty set. How can we do that? Take the solution of the singular problem, put +1 here, and consider this problem here. You can show that this belongs to the dual of the Sobolev space. And here is the extra condition that we had on eta and p and n, the last condition that I introduced in the beginning. Okay, and here you have a simple problem where now you have a maximal monotone operator, a function here that is in the dual of the Sobolev space. This is maximal monotone coercive, it has a solution. Here we use the simple fact that if you have a reflexive Banach space and another Banach space, and the reflexive Banach space is embedded continuously and densely into the other space, then the dual of the other space is embedded continuously and densely into the dual of the reflexive Banach space. Okay, so here, this is what I was just mentioning. And then, as I said, you have a maximal monotone coercive operator, you have a solution which is unique. The solution satisfies this inequality, which in turn satisfies this. And the solution is L infinity. Therefore, this is also L infinity. Okay, now I use the growth condition. And I can find lambda 0 small so that this is true. And therefore I have this inequality here. But what does this inequality tell me? It tells me here, it's missing a me in both sides. This tells me that I have an upper solution to my original problem. The moment you have an upper solution, you truncate at that point. Okay. On the other hand, since f is positive, the purely singular solution is a lower solution. And because of the presence of 1 here, this solution u tilde is bigger than this. So you have an ordered pair of upper-lower solutions. The process is standard. You truncate, you apply a direct method of calculus of variations, and you have a solution. Okay. So essentially, we show that this interval is inside the admissible set, and therefore the admissible set is different from empty. Okay. By standard weak comparison, you have that every solution of the problem is bounded below by the singular solution, the solution of the singular problem. What is the structure of this admissible set? We show that it is connected. Namely, if you have lambda in the admissible set and theta less than lambda, then theta is also admissible. How do we show that? Exactly as before. Okay, you have a solution because lambda is here. You have a solution which belongs here. You know that this solution is bounded below by u bar, the singular solution, and you have therefore an upper lower solution pair which is ordered, same technique. Okay, and you do the calculation, the application of the Weierstrass-Tonelli theorem, and you prove that theta is also in L, the admissible set. Okay, so embedded in that proof is the fact that if I have an admissible parameter and u lambda is a solution to the problem and theta is less than this admissible parameter, theta is admissible too, and you can find a solution which satisfies this. If we were in a balanced growth problem, the conclusion of that problem, of that corollary would have been stronger. The conclusion would have been that u lambda minus u theta is in the interior of the cone C1, which is important. Here, because of the lack of regularity theory, you cannot say that. Okay, we take lambda star to be the supremum of L, and we can show that this is less than infinity, is just comparison principle, a simple application. Okay, and here is how you prove that this is finite. You start with this inequality, which is a consequence of the assumptions on the perturbation F, and then you take a compact subset inside this. You take M0 to be this infimum, which is strictly positive because the solutions are bigger than 0, okay? And then you apply a comparison theorem to this function and this function, okay? Now, if we are in this open interval, there will be two solutions, okay? Let's see how we prove that. Let's take vita to be in this interval here. We know by the connectedness that vita is going to be admissible, so it has a solution. The solution can serve as an upper solution to the lambda problem. As always, we have this as a lower solution, so we have an ordered pair of upper-lower solutions. Again, the same thing, a minimizer, which is u0. If we were in the balanced growth situation, this u0 would have been in the interior in C1 of the order interval with one end this and the other end this. Now we cannot say that. And why this creates difficulties? Because we introduce this, we cut from below the function at the lower solution, and then this function here, we cut it at the upper solution. Okay, and we consider the corresponding primitives, and then we have those two C1 functionals. These two functionals coincide when I am in the interval u bar mi, u vita. Okay. And this functional is coercive, lower semi-continuous, therefore Weierstrass-Tonelli theorem says that it has a minimizer. Okay, and as a matter of fact, the minimizer will be in this interval here. And we can always assume that it is the only minimizer, because otherwise we already have two solutions and we are done. Okay, so this, since it's a minimizer, I have that the critical group is non-trivial only at 0. And now, here is the difficulty. If I was in the balanced growth situation, because I would have the solution in the interior of the order interval, then it would have been a local minimizer in C1 for the sigma lambda functional, and therefore I have one solution, local minimizer. The other solution, using the functional sigma lambda, can be obtained using the mountain pass theorem. And the mountain pass theorem means that the first critical group is non-zero, and therefore it cannot be equal, that mountain pass solution, to this U0, because this U0 satisfies this condition. Okay, now I don't have all that, and I have to show this claim here, which is done by a lengthy and difficult estimation process, where important role plays the fact that it is a locally Lipschitz function. Okay, here I present, as a matter of fact, I have also to truncate it at a big M, and then send M to infinity. Okay, and eventually we end up with this property here, which property says that I have continuity with respect to the C1 norm, but this continuity implies that the critical groups are the same. Okay, so I have these critical groups to be equal. I send them to infinity, and I have this, which proves my claim. Okay. Okay, now there are various ways to proceed. First of all, you have this minimizer, which satisfies this. At infinity, because you are superlinear, the groups are 0, all of them. You apply the mountain pass theorem, and then the Morse relation to get a solution which is different from the original one. Okay, the only thing now left is to decide about lambda star. Lambda star is also admissible. Yeah, it has a solution, something like a bifurcation. Exactly. I take a sequence that approaches the critical value from below, okay? And I have solutions for each one of them. The solutions satisfy this inequality. And since the perturbation is positive, I have this inequality here, which means that this is less than 0. I have this is equal to 0. And therefore, I can argue, as in the Palais-Mail condition, to get a convergence strongly in the Sobolev space, which means that I have a solution for the lambda star.
So it's admissible.
It is admissible, exactly. And therefore, here is the theorem. First, if μ is big, then we can find the critical value, okay, lambda star, for which if I am in this open interval, I have two solutions. At lambda star, I have at least one solution, no positive solution if I am above this. This is global in lambda. Now, to finish, two simple remarks. First of all, is it possible to get rid of the μ parameter? If you remember in the beginning when I solved the singular problem, it was necessary. I don't know if it is possible to get rid of that. Second, if f is not positive, we used it several times in the proof. If f is not positive, can we have such a global description with respect to lambda? Even in the balanced case, we have results with the same authors, but it's not global in lambda. And finally, what happens if eta is bigger than 1? These are called strongly singular problems. With Professor Radulescu and myself, we have a paper, but it is existence. I want to know if I can have a global existence and multiplicity result with respect to lambda. Okay, I'm going to stop here.
Thank you very much for the excellent talk. There are questions, remarks, comments? I have just a curiosity, but maybe there is no answer. I work so much on this type of operators, and when you pass to the Orlich space, you must go naturally to the Q star, which is the smaller critical exponent. Because you do not know how is the region where A is 0. Okay, it would be very interesting to me, but I don't have any idea, because when A is identically 1, I could reach, even in Rn, Q star. And so I was wondering about sufficient condition on A, not so trivial as A equal 1, that guarantees this fact, that means A equal 1 means A strictly positive everywhere. Would be a very interesting point. That's just a remark. Sorry, yes, I know, but that just to thank you very much. Thank you very much. It's for me a great pleasure to introduce Professor Billy Zhang from the Shandong University of Science and Technology, and he will speak about on a critical and singular Kirchhoff-type problem. Thank you very much, Professor Zhang, to being with us.
Thanks so much for your kind introduction, Professor Pussy. Many thanks to Professor Casati for his kind invitation and great help, because I lost my packet, and so yeah. A special thanks to my dear friend Vicentio for his continued encouragement for more than 10 years, because I'm not confident in my ability to study mathematics. So I can very thank here. I take this opportunity to say happy birthday. Yeah. In this talk, I will present critical joint work with Dr. Choi Lei and Professor Radulescu. Okay. Here I will talk about a problem involved the singular and critical nonlinearity in the Kirchhoff setting. I would say I would introduce a new technique to overcome the less of compactness. So here here the domain is bounded, and the gamma is between the 0 and the 1. Lambda is a parameter. Yeah. We know it's difficult to estimate the less valued when we study critical problem. So I will introduce a new technique to overcome. So here we just see some application about the related singular problem. I followed Professor N.Papageorgiou. Yeah. Here is the assumption on the Kirchhoff function. Here we just would like to say we just cover this case. The theta is less than 2. It's not 2 more because we use this condition. Yeah. So the assumption is very classical as is C1 and is positive and increasing and so on. Here's the background for the Kirchhoff model. We would say the two cases is one is no degenerate, another is degenerate. Yes. Here is the degenerate case has a realistic meaning. Yes, thank you. Now I just scanned some related results for the singular problem. This problem is starting from the seminal paper by the Rabinois and so on. A lot of other and paid their attention on this study. For example, is Ladulasu and so on. Yeah. Here, I just want to say my problem is relate his literation. Yeah. Here, without a Kirchhoff function, yes, there are many results and a lot of different methods. For example, is using the superlinear this paper obtained one positive solution and so on. Here is more rich results. Yeah, just scan the results and so on, more regularity and so on, and it's very interesting to estimate the exact results lambda past. Okay. For the general case, yes, we focus this singular problem. Yeah, he obtained the Windic solution. Yeah. Okay, and for the Kirchhoff function, my direct motivation is from this paper because it's difficult. In this paper, it's difficult. They are estimated less valued for the multi-pass solution, but it's mistake in this estimate, so it's difficult to find the less valued. Yes. So in this talk, I will use a new technique to find the less valued. Yeah. Yeah. Here I just sketch introduce the unique result for the gamma is between 1 0 is a weak singularity. So yes, this is a unique result for the gamma is equal 1. Yeah. Yes, is from the fractional setting. I just for the completement. Yeah, here is from the fluid method of super solution. Yeah, the other obtained the following results. Yeah, of course, is the gamma is between more ranges and something more higher regularity. Yeah, and more binary method, and this other obtain 2 positive solution, and a more rich results use the different method. Yeah. Okay, for the Kirchhoff function fractional setting, I just found some paper about this. Yeah. Yes, this is a degenerate case for the Kirchhoff function is take a special fun. Yeah. He established this case is plus, and is involved the critical exponent, and lambda is parameter. Yeah, he used the truncation argument, and he obtained 2 positive solution. Yeah. Okay. Okay. Oh, sorry. Sorry. Okay. Yeah. Later, Fissler and his collaborator, he considered the following the Kirchhoff problem. I would to say he just he obtained 2 positive solution, but when established the multipath solution, he assumed B is sufficiently small, because he can the second solution they have positive energy. Yes, must be less than the less whole valued when he found a path. Yeah, but this assumption limitation is very strong. Yeah. So this something about the strong singularity, and about this superlinear method doesn't work for this case. This is my work about some is we consider is minor, and Q is subcritical and subcritical. Recently, I consider the critical case with my student. We just extend this result to a critical case. So, of course, I consider this case no fractional setting. Yes, using the most rarely, and but we consider just two solutions For lambda is jumped to lambda 1. Yes, between this interval. Yeah. So in this talk, I will discuss these results. We obtain two positive solutions. Of course, the technique, the approach is standard. We found one solution near the serial with positive, negative energy, and we found another solution with positive energy using another solution is multi-path solution. So main difficulties is how to find the threshold value for the energy function. Here because we deal with the singular problem, so the energy is just continued, but not differential. So we one strategy is using the no smooth critical point rarely. Yes, so we introduce the concrete PS sequence. Here is the PS sequence, and concrete PS sequence is weak slope of energy by the following definition. Yes, you're using the Ekelund, variational principle. Yeah. So we would like to find positive solution. So we are working this space. Yes, just the close positive code. Yeah, in this space. So it's according to the definition and so the standard technique, we can deduce the concrete PS sequence is about it. Is easy to solve. So we can show the weak slope is serial. Then U is in a weak solution in such sense. Such sense. Sense. Thank you. So now I just introduced a profile decomposition from this two others in 2007. He defined a group of the scaling operator by this. This group contained all the translation and the duration, and so this. So if the PS sequence is bounded, it has provided decomposition like this. Here U is the weak limit function, and its UK is between this space. Yeah, this space. So there has for many properties. For in particular, is very important is free and for free from the free property, and we can know the index set maybe infinity, yeah, because this is sequence is bounded, so is the set is finite. Furthermore, if we can show, the set is empty, then the weak limit solution is strong limit solution. Now we can find the strong convergent sequence. Yeah. So this is according to so now we just to calculate about this according our setting. We know such result, then we have to pull the bounded domain to the whole space, and so we can obtain such results. So now we can suppose the profiled decomposition hold, then we can prove the index set is infinite. Finite is if we can show the set may be empty, okay, n is equal 0, we can find the strong limit. Now we can transform the new profiled composition. This is bubble is for the elliptical problem as in bubble. So we have a new profiled composition, just like this. Is a weak limit function. Is bubble. Yes, and so we have a couple systems. Yes, we know is more equation, more possibility. So is we can solve it. Also, right? Yeah. We can more possibility. Now we have such a system. Yeah. Then we can transform the critical term or singular term to into the real term. You can use the system. So of course we can find such decomposition. Yeah. Now we decompose the function into yes, you can limit you can force decomposed. Now we can compose. Now we establish the function to relate the weak limit function with yes, with bubble. Yes, we can find this function is the continuous differential. So we can is less than the 1. 1 is the is unique positive solution the equation under our hypothesis. Yeah. So we can have this results. So now we can decompose this function into cut into two functions. The red part is correspond the red part. Then Jn is complete to this part, and the Cn is the last part. Yeah, last. So we can easy to estimate the two function. As a result, we can obtain such estimate. This is Jn is greater to here, and Gn is greater and this term. Yeah, this term. Yeah, we can define the infinite mu, and just we just in the following I would found mu1 is the threshold, just as we need threshold mu1, because from this estimate we can show n is 0. N is 0. If otherwise we can use the above estimate to show this contradiction. Yeah, contradiction. So is n is 0. So we can find the mu1 is exactly threshold value as we want it. Yeah. So we can see the function satisfied the CPS condition at the level C. Yeah. Okay. Mu1 is, of course, is achieved and is less than D. Yeah. So now it's most difficult is overcome. Now we can see lambda is sufficient small. Then we can show the function shift the local minimize, yes, near the zero with negative positive energy, negative, yes, value zero close to zero we can find by. Then we can by the echelon principle, yeah, because showed. Now we just found another solution, yes, small-pass solution. So we use our decomposition technique to do so. Now, first all is we can. Sorry. Sorry. First all, we need to show the level is positive. So we here U is the local minimizer of the function I1. Now we can use the standard technique to show the mu as the mu1 as the exist CPS sequence at the null-pass value. Yeah, C1 start. Yes, so, and of course we need to show the mu1 is less hold valued. There is no, but there is a CPS sequence, but have no conversion the subsequent in no. Of course, we need to show the critical value the level is less than is mu1 is less mu1. So if we consider sufficient small, so we use the bubble, yes, less likely to truncation to fault. Just special. This is the proof. Yeah. We need to estimate the function. This function. So yeah, we can divide it to this part. Yeah. So estimate the C function. C function is we can calculate the C function is at the take the minimize at the T zero. Yeah. So you can easily the C function take value is mu1 at T0. So we can obtain such equation. So we can see the such estimate. So we can see the yes equal here.
Maybe it's better to.
Yeah, it's just okay. The last. Yeah. Now okay. I want to remark our decomposition can deal with many problems. For example, is for just not singular, just below 2 order. Q. This is below 2 order. We can find the minimizer is okay. The minimizer. So and we just use the bubble. Okay. So this is below 2 order. Now, of course, you can consider such nonlinearity. So, of course, we use this method to obtain this question. This question, for example, is linear. The nonlinearity this is linear. So our method is valid to do so. We can consider the disjoint case. General case. We can do much more results. For example, decays and the property and so on. So we obtain two positive solutions between here between this interval here. It's much more rich results. So and finally, I would propose some question. For example, if we consider the gamma is equal 1, this is difficult to estimate the threshold value because the function, the Anderson function, maybe is not continued.
Yes.
It's much more. So for more interesting, we think we consider the sign changing solution is much better to consider. I think so because Professor Zhiqiang Wang used the orthogonal decomposition to consider the infinity many solution, the size changing solution. So they are succeed in using the method, using the decomposition. Now I thank you for your attention. Thank you.
Very interesting talk, very deep proof technique, best compliments. There are questions, comments, remarks, a very short question. Yes, you anticipate with your open question my question. That was the case, gamma equal 1. Yes, that was maybe by approximation and so forth. So thank you very much.
Thank you.
Thank you very much.
Thank you. Okay.
Is a change of program. The next speaker is Professor Goubet from the University of Lille. He will speak about nonlinear eigenvalue problem involving Lipschitzian nonlinearity with non-positive, primitive, and applications. Thank you very much for being with us.
Thank you very much for the introduction. First of all, I would like to thank the organizer for their kind invitation. It's my first time in Varese. And bon anniversaire, Vicentiu. I don't know if you remember this picture. It was 2 decades ago in Romania when we start working with Louis Dupeigne on large solution for elliptic problem. Okay, today I will talk about a conjecture in that is a conjecture in a nonlinear eigenvalue problem for the Laplacian operator, no P Laplacian, P equal 2 in my talk. And I will give some results. And if there is some time, I will give you some application concerning all problem concerning global attractors for damped wave equation that are Sine-Gordon equation. Okay, what is the problem? Consider in my talk, omega will be a smooth bounded domain of Rd with d larger than 2. And we consider Lipschitz nonlinearity. And I will discuss some question about the following problem. Consider the problem minus Laplacian u equal lambda f of u. And I always consider in my talk homogeneous Dirichlet boundary condition. I would like to know if f of 0 equals 0, of course, u equals 0 is the solution, can this problem have a non-zero classical solution? I mean, non-positive solution, but I consider also sign-changing solution. Okay. The classical case that is well studied in the literature, I cannot quote all the people who worked about this problem, is the pure power case. And you know that if you consider an annulus, and for large p, for p large enough depending on the dimension, then there exists radially symmetric non-zero solution to the nonlinear eigenvalue problem. I'm not concerned with this case, but instead of that, I will consider nonlinearity such that the antiderivative of this nonlinearity is always negative. Then you can think, for instance, as this simple function. And the question is there, for instance, to simplify, is there any condition on a domain omega such that there exists a non-zero solution to the problem Laplacian of u equal sinus of u? The statement is very simple. Then I learned this problem on a paper by Biagio with we worked together on this. That is that was published in Archive few years ago. That is for conjecture in nonlinear analysis. It was one of these conjecture. Okay, what is the simplest case? Assume that omega is convex, or that is a star-shaped domain with respect to 0, for instance. You do the usual pose-f method. You multiply by x gradient nabla of u. You integrate by parts. I'll always consider classical solution. And what do you have? You have this equality. And if you look closely to each of these terms, this is non-negative. This is non-negative because on the assumption on the nonlinearity. This is non-negative also. And therefore, all of this term has to vanish. And u equals 0. Then the answer is simple in a star-shaped domain. No non-zero solution to Laplacian u equals sinus u. This is none. The second result in this direction is due to Fan and Riccieri, that they prove that there is no radial non-zero solution of the problem Laplacian u equals sinus u in an annulus. And the proof is simple, because here they assume that the solution is radial. Then you have just an ODE. You have some quantity that is conserved. This is true for any radius R1 between A and B. Choose first R such that U achieves, the modulus of U achieves its maximum at R1. Then this cancels. You have that C is non-positive. Choose R equal B, gives that C is non-negative, then C equals 0. And choosing R equal B gives you U prime of B equals 0. And since U of B equals 0, applying Cauchy-Lipschitz theorem, U has to vanish. Then no radial non-zero solution in the annulus. Okay. Consider now I will relax a little bit my problem, and I will allow the nonlinearity to depend also on x. Okay, it's not where f is always Lipschitz with respect to u. In the following, lambda 1 will be the first eigenvalue of the Laplacian with homogeneous Dirichlet boundary condition, and there is this following result that is due to Fan. He proved that if lambda is larger than this value, this ratio is the ratio of the first eigenvalue and the Lipschitz constant, he can exhibit a function nonlinearity f such that the problem has a non-zero classical solution. And it was known by Richery by using calcul of variation techniques that there is no non-trivial solution for lambda that is below this quantity. Then one conjecture could be that this kind of result can be true also if f does not depend on x. It was one of the conjecture. Okay, then to complicate, or let me give some well-known result. The first one is due to Modica that consider entire regular solution to Laplacian u equals sinus u. And you have a rigidity result that said that if you consider an entire solution that is bounded of this, if by a chance there exists a point in RD, sorry, it's not R, it's typo, such that you have this, then the solution u is constant. And why this is true? This is true to this pointwise estimate that is true and then can be proved using the P method of Payne. Then you have a kind of rigidity result. As a corollary, if you touch 0 at some point, then u has to be equal to 0. It's very close to the Dirichlet problem. Okay. Then a last example, to be more confusing. This is an example of non-zero solution of the equation Laplacian u equal sinus u in RD. Okay, let's now give the first result. I can do some dilation on the domain, and in the following, I will always assume that the Lipschitz constant of the function is 1. And the result is reads as follows. It's close to a Modica result, and it's not. It gives a negative answer to the conjecture state below that says that there is no non-zero solution of the equation Laplacian u equals sinus u in annulus. We know that there is no radial solution, but this result says that there is no solution. Okay, let me try to explain the proof. For the proof, we will argue by contradiction. Assume that there is a non-zero solution. I said that I can assume that u is positive somewhere. If not, u is negative somewhere. And if I consider this function, this is solution to this problem with a new nonlinearity that satisfies exactly the same assumption than the previous one. Then changing problem, I can assume that u is positive. It can be a nodal solution, but it's positive somewhere. Okay, the second lemma reads as follows. This is true for any Lipschitz function with constant L equal 1. You have an upper bound of this function. I don't know this function. I just know it can change sign. That it's sometimes not convenient for proofs. And here you have this upper bound for this function f. If f is C2, this is simple. Let me sketch the proof. You just consider the Taylor expansion of this function. This is bounded by below by this term. And you have this polynomial that is always negative. Then its discriminant has to be negative, then the result. It's easy. Simple proof. Okay, let's move. And the proof relies on the sub and super solution method of Perron. First, I will construct a non-negative subsolution that is positive somewhere. I just have to consider this function. And in what follows, let me set C for the supremum of this subsolution. I have a subsolution positive somewhere. And I will construct now a radial super solution that is above this subsolution. How to proceed? First case, assume that there is a side that is larger than the supremum of the subsolution, such that this quantity is negative. Then you have a constant that is a super solution and that is above the previous. This is simple. A constant is radial. No problem. Assume that this not holds true. Then this function is non-negative for large S. Let's introduce the torsion that is the solution of this problem, minus Laplacian of zeta equal 1 with homogeneous Dirichlet boundary condition. In an annulus, this function is radial. And let's introduce the function that solves this implicit equation. What can we say about this equality? First, this is always larger than C, then this is above, this function is above the subsolution. Of course, since zeta is radially symmetric, then this function is also radially symmetric. Differentiating this equality, you find out this, and for this is non-negative since this is larger than C, then this is non-negative, and you have that this function is a super solution of the problem with the square root of minus 2f. Then this is a super solution for the first problem. Okay, last remark. Since you have that this bound of f around 0, you have that this integral that is reminiscent to the Keller-Osterman condition is diverged. It implies that this function that is radial is bounded. Then we have a subsolution that is positive somewhere, a super solution that is radially symmetric, bounded, smooth, and above the subsolution. Game is over. Now we use the Perron iteration method. We start from the super solution and we solve this recursively, this linear equation. Here, since I assume that f is 1 Lipschitz, you have some monotonicity property for the right-hand side. And you have then, you can prove recursively, this is the classical Perron method, that you have a non-increasing sequence that is above the super solution, and such that at each step, since you start from a radially symmetric function, this is radially symmetric. Okay? You pass to the limit, and this converges to a function that is a weak solution. In fact, due to classical elliptic estimates, this is a classic a solution in the classical sense. And this is non-zero, because this is above a non-zero function, and radially symmetric. Then we can apply Fan-Riccieri result contradiction. Okay? Let's go forward. Okay, this is true for an annulus. And what about more general domains? And we were able to prove that if the boundary of the domain has a non-negative mean curvature, there is no non-zero, any solution to Laplacian u equals sinus u equals 0. Then this is, we were happy about that. This is a general result. For large dimension, there exist such domains that are not star-shaped. And the proof is similar, is the Perron method. And this time we do not construct a radially symmetric solution, but a positive solution of the previous problem, starting from any solution by the Perron method, exactly by the same iteration technique. We can construct a positive, a non-negative solution that is positive somewhere. Then we apply a theorem that is due to Farina and Baldinocci that is close to the Modica result. If this domain has the boundary has non-negative mean curvature, for a positive classical solution of the problem, you have this pointwise inequality. And game is over once again. Why? Because by the strong maximum principle, the function u, that is u on the boundary, is positive inside. By the off-boundary point lemma, you have that this quantity is negative on the boundary. But due to Farina and Baldinocci pointwise, this is 0 also on the boundary, contradiction. Okay, we stop here. And few months later, we learned that there is two Spanish guys that were able to remove the assumption about the curvature on the boundary. I cannot explain the method because I'm not specialist, in fact, in elliptic equation. They use some results about elliptic equation due to Clément, that is a mathematician from the Netherlands. Okay, if you want to learn more about this problem, the final result is due to Lopez Martinez and Molino. Okay, then no non-zero solution to Laplacian u equals sinus u in any bounded smooth domain of RD but 0. Let's give some application now to some wave equation with damping. Here you have the damping term. The parameter alpha is positive. And I will consider, because of the previous result, what is called the Sine-Gordon equation. This is close to Klein-Gordon equation, but you substitute to u minus u cub over 6 this sinus. This was used as a key model for dissipative damped wave equation. And I always consider this equation on a bounded smooth domain of omega with u equals 0 on the boundary. Okay, what can I say? I have, due to the alpha that is positive, some dissipation mechanism. That is this energy. Here you see the kinetic energy, and here's the potential energy. This term is non-negative. That decays along the trajectories because of this non-negative term. In other words, the meaning of that is that this system is a gradient system, okay, because you have some kind of Lyapunov function. Okay, for this kind of equation, there is a general result that is due to Guidaglia and Temam, applying some ideas due to Alain Haro, that this kind of equation have a global attractor that is a compact subset of the energy space that attracts all the uniformly unbounded set, all the trajectories. Okay, I will remind here what is how it is construct a global attractor. Usually this is, you find some absorbing ball, that is a ball of the energy space that contains all the trajectories after a finite time. And the classical method is to consider the omega limit set of this ball. And this is a good candidate to be the global attractor. Unbounded domains for parabolic equations, since you have some smoothing effect in finite time, and since you have a Rayleigh theorem, it's easy to prove the existence of this intersection of compact set due to the compactness of the map that sends the initial data to the flow. S of t is the flow. It's more involved for wave equation. There is a splitting in two parts. A part that vanishes when time goes to the infinity, and a compact part. This is the contribution of Haro, Guidaglia, and Temam for wave equation. Okay, for Schrödinger equation, this works also, but this is another story. Let me give a short proof of the asymptotical smoothing effect. This is more or less equivalent to prove that if you consider a right-hand side that is defined for all t in R and bounded into L2, that any solution to this equation that is defined on the whole line every time negative or positive and bounded in this space in fact more regular than you can imagine. Okay, a short proof. I use a Schrödinger proof. I introduce a new variable v that reads this way. Here is the real part and here the imaginary part. And you can solve your wave equation as a Schrödinger equation with this kind of dispersion. Here, this is a damping term, in fact. And here, you have the nonlinearity, and you see that due to this operator, you have one derivative. Since all global bounded solution reads this way, where this is the free linear semigroup, you have 1 degree of regularity, and proof is over. Okay. Then, now we know that there is a compact global attractor for my sine-Gordon equation. And the good news is that this is a gradient system. Then I know exactly what is the global attractor. The global attractor is only constituted of stationary states and heteroclinic that join the points. And what about for a sine-Gordon equation? The stationary state solves Laplacian u equal beta sinus u. Then there is, we just proved that there is only one point, one solution that is stable, then the attractor is the point. It was not known for this equation. Okay, thank you for your attention.
Thank you very much for your nice, clear talk. There are questions, remarks, comments? very interesting. So
Thank you.
no comment in particular. I don't have any comment. I don't know, Professor. Do you have any comment? No. So let us go to the coffee break.
I did my best to keep in schedule.
How many? No, how many minutes you think?
When
Well,
you-
we resume 20 minutes. So we resume in 20 minutes. Thank you very much for all of you. See you later. Enjoy the coffee break.
Excellent.
Sam,
Let's start again. The next speaker is Dr. Giulio Romani from the University of Studio Insubria and this center, the Riemann Center. He will speak about nonlocal planar Schrödinger-Poisson systems in the fractional Sobolev limiting case. Thank you very much.
Thank you very much for the
You are
introduction.
local.
Exactly.
You are local, not nonlocal.
Excellent. And yes, first of all, thank you for the invitation. It's a great pleasure to be here, and thanks for the organizers of the conference, of course. In this talk, I will present some recent results obtained in collaboration with Daniele Cassani and Jiju Liu from Wuhan University. So let's start from the well-known, well-studied Schrödinger-Poisson system. So this is a system which couples Schrödinger equation on the first line of the system, where let's consider the simplest case of the Laplacian as a driven operator and the potential V, which is, for instance, continuous, bounded from above below by positive constants. And the second equation of the system is the Poisson equation. We study this system in the whole space Rn bigger or equal than 2. And the coupling between the Schrödinger equation and the Poisson equation is via the right-hand side. In the right-hand side, there is a function f, hypothesis on which we will be given later, of course, and the big F is the primitive function of small f. So this model appears in many different contexts in physics, for instance, in electromagnetic fields theory, or quantum theory, or model for crystals, and so on. And in the, let's say, more general case of n bigger or equal than 3, one usually wants to solve firstly the Poisson equation by means of the convolution with the Ritz kernel. And I point out that the Ritz kernel is positive and decaying at 0 at infinity. And insert it in the Schrödinger equation such that one obtains a non-local equation because of this convolution. The advantage of this method is, of course, the reduction between from a system to a single equation, but also because now the Shocard equation in red is variational. So one can study it with variational methods, as is well known. And in particular, this term, which comes from the non-local nonlinearity in the right-hand side, can be dealt with hard-deletable Sobolev inequality. And this is, of course, a not complete list of authors that dealt with existence, multiplicity, concentration, positivity, and so on and so forth. Okay, so, but we are actually interested in the limiting Sobolev case, because it will present some new phenomena. In particular, let's start from the beginning. So the limiting Sobolev case is the case in which the Sobolev space WSP, S is the, let's say, number of derivatives, and P the order of integrability, continues embeds in all LQ, but not in L infinity. And this is the case in which, I mean, this case is when the dimension n is equal to the product between these two indexes, S and P. And so in the local case, if one considers S is equal to 1, and one considers P is equal to 2 is equal to n also, then this is the case that one has when one considers the Schrödinger-Poisson system in the slide before, but in dimension 2. Okay? The analog, let's say, for the case always local, but P is equal to n, in general bigger or equal than 2 or 3, will reflect in the modification of the Schrödinger-Poisson system, as here, where the Schrödinger equation becomes quasi-linear, because we have the P Laplacian, in the case P is equal to n. And the second equation of the system becomes a possibly high-order, possibly fractional Poisson equation, because and it depends on the parity of the dimension n. It is interesting to consider such models in the case of the Sobolev limiting case, because basically two new phenomena appears. First of all, by the well-known Schrödinger-Poisson inequality, one can deal with exponential nonlinearities, and in particular, more important for this talk, the Ritz kernel of the operator, which comes up in the second equation of the system, has a logarithmic behavior. So in particular, it is not anymore true that it's bounded from below by 0, but it changes sign. And in particular, it is unbounded from below and from above. And if we consider the case n is equal to 2, so the classical Schrödinger-Poisson system, but in dimension 2, then a natural choice for the solution of the Poisson equation is this one, so always the convolution between the right-hand side and the Ritz potential. But a first question that emerges is it true that it's the solution in a suitable sense of the equation? I mean, it's of course natural because one considers its kernel, but it might be the case that there would be more other solutions. So these points, which is clear in the case n bigger or equal to 3, becomes a little bit more problematic in the Sobolev limiting case. I will return to this problem later. And anyway, if one chooses that this solution as let's say the solution in some sense of the Poisson equation, one can retrieve the Shocard equation, but now in the right-hand side we have, of course, this convolution with the logarithm. And the problem now is that one would like to deal with these problems in because of the presence of the minus Laplacian in h1/2. But if one writes down the functional associated to this equation, the term of the function which is associated with the right-hand side, which is this one, might not be well defined in h2/2, in h1/2, sorry, which is the natural space in which consider the equation. So this is a first problem, a second problem, let's say, that pops up. And a way out, which was used firstly by Chingolan and Ved, following some ideas of Stube, as already presented by Zhang a couple of days ago, is to consider a constraint space of H1. So we deal with a subspace, a subset of the natural space H1, in which we are sure that this term in the functional is well defined. A second approach was considered more recently by Cassani and Tarsi, and they investigate which is the proper functional space for which this Shocard equation, I mean, the function associated with the Shocard equation is well defined, in a sense that they found a weighted Sobolev space in which for all elements of this space one has a log-weighted Poisson inequality. And this permits to give sense of this term in the functional associated with the Shocard equation. So in these two approaches, the main target was the functional space. There is another approach which Zhang presented to us on Monday, and it's, let's say, dedicated to the study of the function instead of the space, which means that one can substitute or approximate the logarithmic kernel, which is the main problem of the analysis, by means of these kinds of kernels, and therefore study a family of functionals, find critical points for each for alpha small, because this is a convergence for alpha going to 0. And then, of course, one has to be sure that all important constants in the estimates of the operational methods do not depend on alpha, because otherwise one cannot pass to the limit at the end to retrieve a solution of the original problem. The advantage of this method is that one retrieves a polynomial kernel in some sense, because one has to deal with t to the minus alpha, and one can apply the standard hard-deletable Sobolev inequalities. And this is also another way to split, let's say, the positive part and the negative part of logarithm 1 over t. So the two terms that pops up have a sign, and we can control it better than rather than the logarithm itself. Okay, so so far we talk about the local case. So, and since this slide was about a general Sobolev space, even fractional, so the natural question that comes out is what happens when we consider the limiting. So how can we define the proper Schrödinger-Poisson system when one wants to deal with a natural space, which is the limiting Sobolev case for the fractional Sobolev function space. And the model that appears naturally is this one. So in the, again, a coupling between, of course, a Schrödinger and Poisson equation. The Poisson equation is the same as in the local case, but with the general n, while the Schrödinger equation is driven by now a non-local operator, which is probably is too small to read well, but is the S fractional P Laplacian, with P is equal to n divided by S in order to have S times P is equal to n. And so we have three main features that one has to deal with. So again, an exponential growth of the nonlinearity, and this follows by an S fractional adaptation of the Poisson-Rüdinger inequality made quite recently by Parini and Roof. Then again, the Ritz kernel of the Poisson equation is logarithm. But now we have to face the problem that this operator now is non-local, and this will cause a lot of troubles in the variational method. So again, if one considers the natural choice of the Ritz kernel here, one has to study this Shocard equation. So, so first of all, I would like to give some details of what one mean with S fractional P Laplacian. So the definition of this operator is given here for sufficiently regular functions, for instance, C11 lock. And this operator, if U is regular, is defined pointwise. We will deal actually with a weak definition of solution. So we will just use the quadratic form associated with, sorry, this one, associated with this operator. And therefore, we say that one has a weak solution of the fractional Shocard equation if for any stress function in our space, then this equality is true, this identity is true. The first term, as said, is connected to this operator. This comes from the potential, and this from the right-hand side, from the convolution. So by simplicity, we will stay with potential is equal to 1, because it's already quite complicated. But we are we think that all our methods will apply smoothly for instance, a readily symmetric V bounded from above and below by constants, positive constants. And now we stay with the case n is equal to 2, because it's the first step in this to consider this fractional Schrödinger-Poisson system. And with n is equal to 2, at least the second equation remains local. Okay, so this system corresponds to this system, of course, down in R2. Sorry, to this equation now in R2. And the question that we would like to answer are these three. So first of all, this formal reduction from the system to this equation is now formal. It's just formal. So we would like to make this rigorous in a sense that we would like to study this variational, produce variationally a solution of the Shocard equation, but now we would like to come back. Okay, so from a solution U of the Shocard equation, is it always true that U and then phi given by the convolution with the Ritz kernel is a couple which solves the fractional Schrödinger-Poisson system? In which sense? So we would like to have a definition, proper definition of solution for this system as well. Okay, so now that we can move from, so when we will be able to move from Shocard to Schrödinger-Poisson, then we will need to study variation of this problem. And also, we would like to prove some symmetry of solution of the Schrödinger-Poisson system because, well, there is no dependence on x, basically. So we expect the solution are radially symmetric. Okay, so first of all, from Shocard to Schrödinger-Poisson. And this is the definition that we considered for a solution of the Schrödinger-Poisson system. So for the Schrödinger part of the system, we consider simply the weak definition of solution. And concerning the second part of the system, so the Poisson equation, we would like to consider a distributional solution of it. So at the end, the couple that we look for is U would be an element of our fractional Sobolev space, and phi is an element of L1, where L1 is here with gamma is equal to 1. So basically, a weighted Lebesgue space, a weighted L1 space. Okay, so of course we need some basic assumption on the nonlinearity. So since we would like to deal with a positive solution, we consider a function f which is equal to 0 for negative value of t. Then on the R plus non-negative, actually positive, with some behavior at 0, which is kind of natural, and moreover that it is bounded from above by some critical exponential nonlinearity, which comes out from the fractional Trödinger-Moser inequality. And the first result that we present is the following. So under these two assumptions for the nonlinearity, and provided U is a weak solution, positive weak solution of the Shocard equation, then if we define phi of U as the convolution with the Ritz kernel, then the couple U, solution of Shocard, phi convolution with the Ritz kernel, is a solution of the Schrödinger-Poisson system, and in particular, in the sense given in the slide before, and in particular, U is also bounded in R2, locally Hölderian, and phi of U goes to minus infinity for large values of x. Actually, we are also able to detect, let's say, the first term of the expansion to minus infinity, to this decay to minus infinity. And the main point to prove this is so the key step is this inequality star. And if you remember the work of Castagna and Tarsi that was explained a little bit in some slide before, this one, they detected a correct Sobolev space in which a log-weighted Poiseuille identity inequality holds for all elements of this space. Of course, this in the natural space, in our fractional space is not anymore doable because of this problem in the functional of this log. But at least for solution of this Shocard equation, we are able to prove the same inequality. Of course, is a restrictive result, but it's exactly what we need since we deal not just with the solutions. And indeed, once we have this, by a result of Heider, we know that all solutions of the Poisson equations are all the form, this model solution, plus a polynomial of degree at most 1. And by this inequality star, we are able to say that the difference between this model solution and our solution, this our natural solution, is simply a constant. Actually, it is exactly up to a constant, this term here. But we know that this is finite, so and therefore the difference is just a constant. So in particular, phi of U is a solution, in our sense, of the Poisson equation. And in order to prove this step, one has to prove, first of all, that you are bounded by Nash-Moser technique, and then some decay estimate at infinity for the solution of the Shocard equation. Okay, so now we can move from Shocard to Poisson, Schrödinger-Poisson system. So we can prove existence for Shocard now. Of course, one asks, what about the other arrow? So is it true that the two problems are equivalent or not? So with equivalence, I mean that if we find that U phi is a solution of the Schrödinger-Poisson, can we say that U solves the Shocard equation, but phi has to be the convolution with, sorry, this, of course, should be convolved with f of u. So the convolution with its kernel. Actually, we are not able to give a proof of that. And the main point is that in our result, phi of u does not go to 0 as x goes to plus infinity. It decays to minus infinity. So if we imagine to add some constant to phi of u, then they will have the same behavior at infinity, because you cannot detect adding a constant or not to a convolution with decays to minus infinity. And this is the main obstruction to prove also the other arrow. So this is still an open problem. Still, in order to solve the Poisson equation, we just need a first arrow, so we are fine for our purposes. Okay, so before going into the existence part, I would like to give you also the result of this, the symmetry result, which says that a solution of the Schrödinger equation will be radially symmetric about the origin, monotone decreasing along the radius. But we need to assume some regularity of the function, which a priori. Because so far we just know that they are just C0 alpha lock and not C11. But this is motivated by the fact that we apply a moving plane method, and the regularity assumption, the further regularity assumption that we need, is needed in order to convert, let's say, this operator from the weak definition to a pointwise definition, to work with operator applied to U pointwise. Okay, and another open problems that appears naturally, what about the radial symmetry result without this further assumption? Then the moving plane method fails in some way, and we are not able to deal with that. Okay, so at last, the existence part. So as I said before, the Shocard equation is formally variational by means of this, functional, but the green term is troublesome. And therefore, we apply the strategy of Liu, Radulescu, Zhang, and Zhang by approximating the log by these polynomial kernels. And therefore, we restrict our attention to these approximating functionals, where we replace this log by g of alpha, which is defined here. And as you may see, we have a positive term and a negative term, which is well defined now in WS2 over S. So, of course, we need some more assumptions on the nonlinearity. The first two are the same as before. So again, 0 in the negative axis, positivity, some behavior near 0, and the fact that f should be either subcritical or critical. Then the f3 implies in particular that the function f is monotone increasing, and we have a sort of Ambrosetti-Rabinovitz condition. The f4 is a little bit more strict. It's an assumption at infinity, which tells us that the function grows exponentially. It might not the case that it's exponential critical growth in the sense of Schrödinger-Moser, but at least exponentially. And the last assumption, which in the model case is quite always verified, is related to the Figueredo-Miyagaki roof condition, and it will be essential to prove to control, let's say, the mountain pass level in order to stay under the critical level for compactness. So the existing results read as follows. So assume that the full set of assumptions for nonlinearity is satisfied. Then the Shocard equation has a radial solution, which is positive, and well, decays also to 0 at infinity. And such that a posteriori, the term that we were not able to justify for the whole space, for this solution, then it is finite. Well, in this statement, the positivity part is simply a consequence by the stroke maximum principle for the SP Laplacian, so it's not a problem. And once we have this existence for the Shocard, since we can move from Shocard to Schrödinger-Poisson, we can reach also the existence statement for the Schrödinger-Poisson. In particular, also the description we obtained before about boundedness of the solution U and the fact that phi of U goes to minus infinity as for large values of x. So I would like to spend the last slides for a very brief sketch about the proof of existence. So first of all, and also because we want at the end a radial solution, we restrict to the radial subset of our space, and this gives us, by means of symmetry, this gives us some compactness embedding in the Lebesgue spaces. Then it is not difficult to prove that the functional J alpha for any alpha fixed in between 0 and 1, so the approximated functional, satisfies a mountain pass geometry. And this permits us to obtain some Palismanic sequence, actually a Cerami sequence we will need. At this point, we need to show that this UN alpha, so for any fixed alpha, this UN is bounded in some norm, so such that we can go to the limit for n goes to plus infinity. So the first step is to estimate the mountain pass level. And this is the estimate that we are able to obtain. And then notice that this estimate is independent of alpha. So this is the first step then in order to prove convergence then for alpha going to 0 as the last step. And in order to estimate this mountain pass level, the last assumption on which I commented before is an essential ingredient. So then we are able to prove uniform bounds. This is the norm in our Sobolev space, Ws 2 over S over 2, which again are independent on alpha. And the common strategy is to have a connection between the functional on the Cerami sequence and the derivative of the functional in the Cerami sequence. But this link is not the usual one when one has to deal with positive kernels. We have some problems in the standard argument, while if you write down what are the functional and the derivative, the only big difference between the two are these two terms. And one has a big F here and a small f here. Sorry, this should be a test function. So in order to link these two terms, one has to choose a proper test function, which is exactly modeled on f on the Cerami sequence by small f on the Cerami sequence, so, such that we have the link between these two terms. And as a last step, in order to prove then convergence for n going to plus infinity, we have to improve a little bit the regularity of the right-hand side, to say. And in particular, we need that the function f on the Cerami sequence is uniformly bounded in L kappa, with kappa in an interval, a small kappa greater than 1, but again uniformly bounded with respect to alpha. And this will be then used for applying some Hardy-Sobolev-Littlewood inequality at some point. So we have we need some space, kappa more than 1. And this is obtained by means of another carefully chose the test function, so we need to modify the Cerami sequence in this way, such that the new sequence has norm in our fractional Sobolev space less than 1. And if we have this, then also we can choose a little small k, such that this is also less than 1, and play with Schrödinger-Moser, well, for the fractional Schrödinger-Moser inequality by Parinian roof. So with all these ingredients, then we can pass to the limit, obtain that for any fixed alpha, there is a critical point u alpha. And then, since our estimates are independent on alpha, and this is a crucial point in our proof and quite delicate, we can also pass to the limit for alpha going to 0. And a posteriori satisfy this inequality, which was the main problem at the beginning. So this is more or less what I wanted to say you, and I thank you for your attention. Here there is the reference for our submitted paper.
Any question, comment, remark? Very interesting.
Thank you.
Proof. Well, no any specific question. Was very clear. Best compliments,
Thank you very much.
I would say.
Thank you very much.
I would say best compliments, very clear exposition, many thanks. Very deep results. Thank you very much. It's for me a great pleasure to introduce the last speaker of the conference, Professor Henri Berestycki, who is the head of the Centre d'Analyse Mathématiques Sociales in Paris. He will speak about the stability-compactness method and qualitative properties of nonlinear elliptic equation. Thank you very much, Professor Berestycki, for being here with us.
Thank you very much, Patrizia, for the introduction. Thank you very much to the organizers for, first of all, organizing this meeting, this wonderful meeting, and also for inviting me. I'm very, very happy to be here. Thank you, Daniele, for all what you're doing in this center with your infinite energy and not renormalized. In fact, it's not the first time I'm speaking here. It's the first time I'm here, but it's not the first time I'm speaking here, because a couple of years ago, when the pandemic started, Daniele put up a wonderful 1 day or 2 days, in fact, meeting, which brought together mathematicians, that was I, and philosophers, and some other, and some journalists also, and we spoke about the role of modeling and how to understand pandemics. So it was a very, as always what Daniele does, was an extremely interesting occasion to confront points of view. And I remember I spoke about epidemics as a mathematical object, which I'm very happy to discuss with you some other occasion. So today, of course, it's also an extraordinary pleasure for me to speak about, the occasion of this meeting, in honor of the tribute to Vincenzo. And as Vincenzo recalled yesterday, we are brothers, mathematical brothers, of course, and our common father is Chaim Bresis. So here you have a wonderful picture of Vincenzo with our common father, Chaim Bresis. I was also a student of Chaim. And indeed, Vincenzo recalled several times the extraordinary atmosphere that was in Paris at the time of when he was a student still, and I was just starting my. I'm a little older brother. When I was starting to work in Paris 6, Sorbonne Université now, as a researcher, CNRS researcher, then professor. And several of you here, which I'm very happy to see, Ugo, Gianpaolo, remember this atmosphere, which was quite particular. It was really something, and I think we learned a lot from Chaim, and I think Vincenzo showed in his career what a great student he has been of Chaim, because he has taken from Chaim many aspects, the elegance of mathematics, of course, the incredible productivity, the number of articles written by Vincenzo is staggering, but also a form of generosity, which I think is very much, we learn very much from Chaim, generosity to share mathematics, to really, Chaim is someone who really wants other people to understand what he's doing, not to impress. And many mathematicians like to give talks where they make sure that no one understands part of what they're saying. We know that. I know several who really do that on purpose. And Chaim is really on the opposite side. He really wants you, he's going to be very unhappy if you don't understand. He really will insist, and even if you have an urgent appointment, he will keep you in his office and will insist on you understanding something. So Vincenzo, I think, has taken this point, but also he has taken another trait of Chaim, which is his extraordinary dedication to international cooperation. So Chaim was nowadays a little bit less obvious, but was an indefatigable traveler, and really has fostered a lot of cooperation. And Vincenzo does the same, bringing China closer to Eastern Europe, which is a remarkable feat. And so in this respect, I'm very proud to be your brother, Vincenzo. Okay, so let me tell you for the next 2 hours. I always like to make the chairperson a little bit nervous. I know it takes much more to make you. It takes much more to make you nervous, I think. So I want to tell you about developing one instance of this. I want to tell you about something which we now understand as a rather general method. This is really a general method of how to prove certain qualitative properties of semilinear elliptic equations. Qualitative properties, in particular, here I'll speak about uniqueness, but it's not only about uniqueness, it's also symmetry properties. We heard in the previous talk about how the moving plane method yields symmetry properties, and but also stability properties and other qualitative properties. And we now understand this as part of a general approach, which I think is very useful to understand it in this generality, because I think it's something that can be applied in a rather large framework. So today I will speak about this. I will speak about uniqueness questions, and the type of question I want to understand today is stationary states of reaction diffusion equation. And I don't know if this is working. Yeah. Yeah, okay, it's true. Yeah. Okay. Yeah, this of course doesn't reflect laser. Yeah. So I'm talking about this semilinear elliptic equation where it's Laplace u equals f of u with u positive. And the main point here is that we want to understand this equation not in Rn, as is usually the case for reaction diffusion equations where one wants to understand propagation, but we want to understand the role of geometry also. So we have a domain. This equation is set in a domain omega, and there is a boundary condition, of course, on the boundary of omega. Okay, and we are looking for positive solutions, positive and bounded, of course. And f will always be positive here, but I will make it more specific in a minute. And so type of boundaries, so there are various types of reactions F. I'll come back to this. Various types of domains omega, and various types of boundary conditions. Dirichlet, when there is it's like absorbing boundary if you want. Neumann with no flux, and something intermediate, which is Robin type conditions. I'm going to talk here really about Dirichlet conditions. So the Dirichlet condition. Neumann is easy in some sense. It's well understood. Robin is wide open for some of the things I'm going to say. Surprisingly, some of the questions I'm going to talk about today are just basic questions where one wants to understand. Neumann is easy. We managed with a lot of work to deal with Dirichlet conditions. Robin needs to be understood. In particular, this is related to the fact that for those of you who have seen it, the method of moving planes is, and I'm sure the previous speakers know that, the moving planes method stops short of working for the Robin conditions. And Neumann, we do it with different approach anyways, just straight maximum principle. So here I'm going to talk about the Dirichlet condition. And in fact, I'm going to talk only about something which is called KPP type of nonlinearity, so coming from the Fisher KPP equation. And because just to limit the talk within the 2-hour slot which has been allotted to me, I'm only going to talk about the KPP reaction terms. But in a paper we are presently finishing, we have very general results for general positive F. And other cases still need to be understood, like bistable and things like that. But let me restrict myself to the KPP. So what is KPP term? Okay, so KPP term is this. So positive, first of all, positive means the solution F is positive between two states. Let's call them 0 and 1. And always positive, and vanishes at those endpoints, 0 and 1. And I will always assume that there are positive derivatives here and there. Okay? And there, in fact, in general, for the reaction diffusion equations, what is called Fisher KPP. KPP stands for Kolmogorov, Petrovsky, and Piskunov. Both Fisher and KPP introduced these equations independently in the 1930s. It's extraordinary, by the way, one in Moscow, one in the UK. And it's really quite extraordinary. KPP, I mean, Fisher was really also, the statistician Fisher was also a geneticist. They were led to this problem because by consideration of how genetic trait spreads spatially. That was the motivation. And the KPP paper is an incredible paper because, as far as I know, it's the first paper to consider parabolic semilinear equations, or in fact, for this reason, also elliptic semilinear equation in the 1930s. And they introduce a lot of things, like certain comparison principles, maximum principles, certain arguments which are still today. There are a lot of things to be understood in this paper. You can learn a lot of tricks of nonlinear analysis in this paper. It's really an incredible paper, the KPP paper, written in French, by the way, which just makes it, with some mistakes, but it's really nice. So there are two cases. So what's usually called KPP is what is called weak KPP, because that's what all you need. All you need is this comparison of the graph of F with the tangent at the origin that allows you to linearize everything here, and this yields what's called linear determinacy of the speed, of the spreading speed. Most properties are obtained from this Bramson shift, from probabilities. A lot of works in probability theories nowadays about this equation. And the original KPP paper had this assumption that, so concave F if you want. So to be more specific, it assumes that the intercept of the graph of F decreases with the point you are intercepting. Okay? So F of S over S decreases. This is what I call strong KPP. It implies, of course, weak KPP, that F is below the graph, the tangent at the origin. Okay? So this is what I call weak KPP and strong KPP. So let me start with bounded domain. So I want to understand the question of uniqueness. Can you say solution is unique? So there are two results I want to recall about the bounded domain case. First of all, the first result is that if you take an arbitrary bounded domain omega, then you can always find an F, positive F, for which you have multiple solutions. You can always construct an F which is going to be positive. In fact, you can even choose it to be of the weak KPP type. You can find an F which is going to be like that, and for which you have multiple solutions. So in the bounded domain case, uniqueness just doesn't hold. And the F you can construct to do that is an F like that. It's a camel hump if you want. And it's an F with two humps, one which is like that and then like that. Of course, this is a weak KPP type nonlinearity, right? Now, the reason why you can construct multiple solutions is clear from the picture, because you can, you construct first a solution, takes values between 0 and this point here, and you do that because you consider it almost as just one hump. And the maximum principle will tell you that the maximum of the solution will be away from this point. And then, instead of going to 0, you make it turn here and you make it an even bigger bump. So when you minimize the energy, you will find a solution whose maximum will be closer to this point. So you have two solutions. Okay, so that's very natural. So you see the weak KPP doesn't have uniqueness in the bounded domains. But then the strong KPP does. And so here's a result which is due to Paul Rabinowitz, JD 1971. Many things are due to Paul Rabinowitz. And it was a little bit my master also in some sense. So he proved this. He proved that when omega is a smooth domain, so it's C2, I think is this result. If omega is C2 alpha, maybe. If C2 is a smooth domain and bounded, then when it exists, the positive solution U of this problem is unique under the strong KPP assumption. So you see strong and weak are very different in this respect here. And I want to give you the proof of this. Okay, I want to give you the proof, because we're going to show you how one can extend it. So let me take two solutions, U and V. And the first observation is that you can always take a multiple of one and put it above the other one. This requires a proof. It's related to the fact that you have Hopf lemma at the boundary. So because you have a positive slope, if you had a zero slope, you couldn't do that, right? If you have zero slope, then you can never do that. But if you have positive slope, a large enough multiple of one will supersede the other one. So that's the first thing. The second thing is that then you take alpha star to be the smallest such value of the multiple alpha for which V is less than or equal to alpha U. You take alpha very large, you have alpha U sitting above V, you reduce alpha to the minimal position. Let me call alpha star the number. Then, by continuity, of course, you have V less than or equal to alpha star U. And my claim is that alpha star is less than or equal to 1. And to do this, we argue by contradiction, assume that alpha star is strictly larger than 1. And then look at the equation that alpha star U minus V satisfies, right? This positive function. It's alpha star f of U minus f of V. And here you use the KPP assumption. Alpha star f of U is going to be bigger than f of alpha star U. This is the consequence of alpha star bigger than 1. And it's really exactly the KPP assumption. I can write it, if you want, f of alpha star U divided by alpha star U less than alpha star f of U divided by alpha star U. Okay, so this is what you get. So therefore, this is not a positive. I don't assume f to be decreasing or increasing, but it certainly is a multiple q of x. When I write this term here, I can also write it as q of x times alpha star U minus f of V. This is intermediate. This is a mean value theorem, if you want. Okay, and q in L infinity is a continuous function. So therefore, it satisfies an elliptic equation with a zero order term, which we don't know the sign, but we know the sign of alpha star U minus V. So the strong maximum principle then tells you that if this is true, then alpha star U minus V cannot touch 0 inside, and the derivative cannot touch 0 on the boundary by Harnack, by Hopf lemma. Thank you. And because of that, then you can again put a small multiple of U below it, because again, it's the fact that the derivative is strictly positive tells you that. So you can put underneath a small epsilon times U below this. But then that's a contradiction, because then you would have alpha star minus epsilon times U bigger than V, which contradicts the definition of alpha star as the minimum. So this is a contradiction, therefore alpha star is less than or equal to 1. So this tells you V is less than or equal to U. If you give me two solutions, then the second one is always less than the first one. Of course, this means that there is only one solution. Okay. And if you read this proof, this is a Paul Rabinowitz proof, and it uses Hopf's lemma, so it's really done in a smooth domain. But if you read this proof, it's very much the same thing as the moving plane method, for those of you who know that. You know, you have a one-parameter family. You take for some range of the parameter, you have an inequality, and you bring it down to the minimal position. And there, the strong maximum principle tells you that if you don't get what you want, you can continue a little bit more. Therefore, it has to go all the way down to where you want it to go. And it's the same thing. So that's why what I'm going to tell you is, in fact, a general version of this. Many different methods, including the moving plane method, into this one framework. Okay, so the question, sorry, the question is, what can you say about general domain, unbounded domains? I'm not going to talk about general positive F. Let me just say that this example we had for the hump, double hump, for instance, in graphs, in domain bounded by graphs, in one domain, doesn't exist. We have I don't have time to go into this, but there's really surprisingly general results of uniqueness for any positive F in a domain bounded by a graph. This is something we started to work with Louis Nierenberg and Ruiz Caffarelli, but we now have much more general results. All this, by the way, is joint work with Cole Graham, who is a young NSF researchers at Brown University, NSF postdoc, whom I met in Stanford when he was doing his thesis. So, okay, and this is what we are doing with ongoing work with Cole Graham about this. Okay, so what is the question is, what can you say about unbounded case? Let me stick to the strong KPP case. What can you say about general bounded? Can you say that? So this, we are talking about the strong KPP assumption. Again, the intercept here, f of s divided by s, decreases as s increases between 0 and 1. And we get the general result there, but we need one more non-degeneracy assumption. So we get, in some sense, generic result. And let me try to explain this result we get. So for this, we need an understanding of spectral properties. So spectral properties. So how do you define the principal eigenvalue in a domain, an unbounded domain? So for self-adjoint operator like what we are considering here, it's easy. If you take any weight function, any potential like V before in the previous talk, any potential Q in L infinity of omega, then the principal eigenvalue of this minus Laplace plus Q in a domain omega, so associated with Dirichlet condition, but we don't talk about Dirichlet condition because we don't know anything about the smoothness of omega, so a general open set, is simply the infime of the Rayleigh quotient, the usual Rayleigh quotient, integral of gradient W square plus Q W square divided by the integral of W square, and you take the infime over all W in C infinity with compact support in omega, for instance. That would be the same. I'm not going to talk, although we use in our proofs, we use several other further properties of this that we glean from previous works I did with Louis Nierenberg and Raghuvaradan about what's the principal eigenvalue in general domains, but also what we do in unbounded domains, which is joint work with Luca Rossi from Rome 1, and where we study specifically unbounded domains. And let me also say that we also use the fact that this lambda 1 is the limit of the principal eigenvalues of in a bounded domain omega intercept with a ball of radius r, as you let r grow all the way to infinity. So this is a result that Agman was, I believe, the first one to observe. So here is so let me not talk about the, okay, let me talk about the, no, let me not talk about this. So let me tell you about the generic result. So for the generic result, we need to understand what's the behavior of omega at infinity. So the difficulty, let me just explain you what's the difficulty in this Dirichlet problem. In the Dirichlet problem, you have two competing effects. One is the fact that f of u is positive and tries to grow, tries to bring you the solution towards 1 and tries to grow the solution. And the other one is that you have the boundary, where the boundary is absorbing, so it tends to take the solution to 0. And the Dirichlet problem, that's the reason why it's difficult and more complex, is that it really combines those two effects, okay? So the absorption from the boundary and the growth because of the reaction term inside. And when the boundary is too close to everywhere in the domain, you won't have solutions. When the domain is sufficiently large, you may hope to have solutions. And this is what I just did not show you. Existence is really based on that. But for uniqueness also. And for this we need to, so in some sense, well, we need to define, the domain being sufficiently large and sufficiently, or not so sufficiently small in some sense, so that you have, but in an unbounded domain, you may have branches. You may have a lot of different complicated crazy behaviors. You may have branches going to one side becoming very thin, other branches, cones starting from the domain becoming very large. And so you need to understand what is the limit at infinity of this. And this is, we understand this through a spectral condition. So this spectral condition is this. We say that we consider all possible limits of omega. So for instance, if you take omega with different branches, so a limit will be what you see in the end, so it's pointwise limit. It's not uniform, never uniform, but of the domain. So you take translations, and you look at the limit, and you take as a connected component. By the way, the limit may not be connected, because think of a U channel like that. If you go and take the limits, so those are two disconnected tubes, if you look at the pointwise limits. So by limits, I take only connected components of this. And all possible connected components are called connected limits, and we look at the principal eigenvalue in each of these components. Okay, and this we call the principal limiting spectrum. So it's the principal eigenvalue of minus Laplacian in omega star for any possible omega connected limit of omega, so including itself, including omega itself. If you take a sequence of points that's just stationary, you get the domain itself. It has an eigenvalue, but then you took also out all possible eigenvalues. And here's the main result. Suppose that F is of strong KPP type, and that omega is strongly non-critical in the sense that F prime of 0, not only F prime of 0 does not lie in the limiting spectrum of omega, but only doesn't lie in the closure of the limiting spectrum of omega. So you want to have a gap, you want to have a spectral gap when you go. So certainly, I'm going to show you some pictures in a minute, you will see what I mean by that. So if you assume that F prime of 0 is not in does not show up in one of those limits as an eigenvalue, which is, this is a non-degeneracy condition, then the solution, when it exists, is unique. And so indeed, it's quite a generic result, so we are able to extend this result, but through this condition, and we have we have a conjecture that, in fact, this non-degeneracy should not be there. It's probably true even without this non-degeneracy. But at this point, we don't know how to prove that. So you have many young people here. I invite you to prove me wrong and give us a simple proof of this, which would be nice to know. We'll have worked for, we've done a lot of work, but still the method is useful in any case. So here is the non-degeneracy condition. Look in the plane, okay? Let me give you an example of the plane. In the plane, let me use this example like a comb. This is a comb, okay? You have the domain omega, and you have teeth coming out of the comb, okay? And in the plane, so each teeth is like a channel of width hi, hi plus 1, etc. And the non-degeneracy condition in the plane, so you know what the principal eigenvalue of the Laplacian is in a strip. So the degeneracy condition means exactly that the infimum of this hi minus pi over square root of f prime of 0 is strictly positive for this comb shape. So that's the non-degeneracy condition. If one of those is just equal to pi, or if you have a sequence of t's for which it converges to 0, to the hi converges to pi over square root of f prime of 0, this is critical. Okay, so we have this. It's not, as you can see, it's a generic condition. Okay, let me just give you in 1 minute the sketch of the proof, because it follows. I just want to highlight how you have to modify the original argument of Rabinowitz. The main point is this one. if this f prime of 0 is not in the limiting spectrum of minus Laplacian omega, then, as I say, all possible limits of omega will have a spectral gap. So it will either converge to something which has an eigenvalue below lambda 1, below f prime of 0, sorry, or they will converge to lambda 1, to a domain which has a lambda 1 above strictly f prime of 0, and there is room here as f prime of 0 minus delta, f prime of 0 plus delta. So because of this, we can decompose the domain omega as a union of two smooth open sets, omega plus and omega minus. And omega plus will satisfy that the principal eigenvalue of minus Laplacian omega plus will be strictly above f prime of 0, whereas for omega minus, all possible limiting spectrum, connected spectrum in omega minus will be in the set 0, f prime of 0 minus delta. The closure of this set will be contained in this set. So we have this decomposition. That's by no means obvious, this decomposition. It's really not a simple thing to say. So heuristically, this is what I call stable compact. So omega plus, I would like to think of it as a stable part. When lambda 1 is positive, it means that 0 is a stable solution. When lambda 1 is negative, it's a non-stable solution. So the part where lambda 1 is positive, I call it stable. The other part, for some other reasons, I call it compact. Bear in mind that it doesn't mean that the set is compact. The omega minus in general will not be compact. You will see this in a minute. But what we will know, because of the fact that the spectrum is away from f prime of 0, you will have compactness-like properties. So you will know, for instance, that it cannot converge to 0 there. Okay? So when, in other words, when the domain, for instance, if you have a channel, if the channel is large enough, the solution will be bounded away from 0. If it's narrow enough, you may have convergence to 0. So that's a difficulty in unbounded domains. So you may have a channel which is large and a channel which is narrow on one side. So one side goes to 0. So the fact that it goes to 0 is that this is what prevents you from applying Rabinowitz methods. Because when you say V is less than or equal to alpha u in an unbounded domain, it's hopeless. So, but stability saves you a day. So let me just say that it's a very delicate decomposition, this one. It's by no means unique, and omega minus, omega plus overlap. I mean, all this. But the fact that you have this decomposition, to obtain it, we use a wonderful result of Elliott-Lieb from 1983, which was published in Invenciones, which apparently has been a bit forgotten, but it's a really remarkable result. It says this. It says if you look, take the lambda 1 of minus Laplacian in a set A, and then you take another set B, and you want to look at how you can approximate lambda 1 of A intersect of lambda 1 of A by lambda 1 intersect B. So usually you cannot do that. But if you are willing to shift the place where you put your B, so, you know, A intersect B is like a window of A. You take a window. But you may move this window by shifting the center of the set A, B of x. So if you are willing to shift the center, then you get lambda 1 of minus Laplace in A up to the error lambda 1 of minus Laplace B. So in particular, if I take B a ball of radius r, this means that lambda 1 of minus Laplacian in omega is the same thing as the infimum of minus Laplacian in omega, where I look at windows of radius r, but I take the infimum of all possible positions of this ball of radius r, and I get an estimate up to error r minus 2. It's a fantastic result, not at all obvious. It's a very, very beautiful result of Lieb. And this allows us to do this thing. So here as a decomposition, I give you a few examples. So of course, unbounded domains can be quite crazy. You can start playing with all possible things you have in mind. So here's a domain where you have, you know, narrow followed by ample domains and so on. So here you will take all the narrow parts. This will be omega plus. Narrow, lambda 1 is positive, means lambda 1 is big, means that you are close to the boundary. The smaller the domain, the larger the lambda 1. So the narrow part is where lambda 1 is big, and the ample part is where the domain is small. So here's how you take, so omega minus doesn't need to be connected, neither does omega plus, but that's what you get. Because remember, we take connected limits. This is a domain, so large, large, narrow, narrow, and you want to avoid the critical case, okay? This is what you get. And the solution is, the equation is this one. The solutions cannot vanish at infinity in omega minus. This is a compactness part in some sense. And the compactness part, when the domain is large enough in some sense, you can use U over V, you can estimate U over V and say it's bounded, like you did, you know, with the Hopf lemma. So just take limits in some sense. You need to take limits and argue by contradiction, and you get this. So in omega minus, you can do that. But you cannot do that in a region where lambda 1 will be small, where the domain will be small, lambda 1 will be large. Because as the solution goes to 0 and you are stuck. So in omega minus, uniqueness proof goes through because U over V will be still bounded. And those, even though omega minus is never compact in this game, usually it's not, but the compactness result will remain true. And then you look what's happening in the narrow part, which is what we call the stable part, lambda 1 positive. Because lambda 1 is positive, then the linearized problem has maximum principle. You know, lambda 1 positive is the same as having the maximum principle. If you, okay, you need to make this precise, but that's what you say. So therefore, what you have gained from the compact part, you can then use as a boundary condition for the omega plus set. And this we have compact. So you first do the compact part, you compare, and then you use the stable part to do this thing. And this is what we call stable compact method. And this is quite general, in fact, for, as I said, to study qualitative properties, to decompose domain into two parts. But you know, it also applies to many other situations where you have variable coefficients instead of domains. But never mind. So one is the domain where you can apply the maximum principle, and the other one where you deal with compactness. And on the part of compactness type properties, then you want to do with a certain, you have to introduce a method. So what I showed you was this, what we call scaling method. So what I showed you here, you know, you compare U and alpha V. But in other situation, you do moving planes. Maybe I'll show you in a minute what I mean by that. In the version that I gave with Nirenberg, we have a version of this which relies on the maximum principle in narrow domains, which is the more general form of this. And or sliding method. In domains bounded by graphs, we use sliding. Or we can use dilations. So all the other methods you want to use that will bring you one parameter family, you deal with first on the compact part, and then you use the maximum principle on the stable part. And this decomposition is what gives you this. So let me give you just, if I can, 2 minutes to show you this. You
still have 1 hour and a half.
Thank you. You're very generous, Daniele. Maybe too much. Don't tempt me. Okay, so maybe. Okay, very good. Fantastic. Okay, so fantastic. Thank you very much. It's really quite elaborate, this system. So let me come back to this here. And so the moving plane method is this, right? Okay, so let me take here the pen. So you have a domain here which has a certain symmetry, right? So let me call this x1, for instance. And you have a solution of the equation minus Laplace u equals f of u and with u positive in omega, and u equals 0 on the boundary. So I'm thinking of bounded domains, okay? In the original method of Alexandrov, as the way it was used by Serin in particular, was the one who brought it to seminar equations, and by Nirenberg, the domain was assumed to be smooth. And smoothness played an important role because you used various forms of Hopf lemma, even some more elaborate forms. In fact, what we did with Nirenberg was also to get rid of completely of any smoothness assumption. So in particular, it works in a square, which was not known before because of the angles. So what we do in this moving plane method is, you know, many of you know that. Let me maybe change the color. And you take a point here, you reflect in this point here. So this is point x, you call it x lambda. This is t lambda, and you define v lambda of x to be u of x lambda. It's because of the Laplacian, you have the same equation satisfied by this, you know. And what you do is you look at the equation satisfied by w lambda of x, which is v lambda minus u. And you want to show, so it's u of here minus u of there. And it's defined in this set here, which we call omega lambda. Okay, so I was trained by the gentleman there. Thank you for thank you for training me with this. So yes, right, it was an intensive course. Okay, so this, let me just show you this. So you want to show that this goes through all the way to the maximum position of symmetry. Once you know that, then you know that u on the left is less than u to the right. And of course, if you start from the other side, you get the opposite inequality, so you get symmetry. That's the way you get symmetry. But it's the same idea. What I want to insist here, this lambda parameter is the same idea. So what we did with Nirenberg was to do this. Suppose you reach an obstacle before you go to maximum position. Then you have a position, and because by continuity you will have that v lambda, what I call v lambda of x, will be strictly bigger than u of x. So v here will be strictly bigger than u there. And on the boundary of this domain, in this cap region here, so let me call it sigma of omega, on d sigma lambda, v lambda minus u is also greater than or equal to 0. Why is greater than or equal to 0? It's 0 here because this reflection is the same point. And here, you take a point here where u is 0 and you reflect it inside where u is positive. So the difference is positive. Okay, this is the thing. And what we did was this with Nirenberg, was to take a domain, carve out here a piece of domain. My drawing is becoming really bad. I should change color maybe. You carve out this domain here, so compact set K, and you say on this domain, this is a compact set. On this domain, infimum of v lambda minus u is strictly positive. This is compactness. And what is left here is a narrow domain. So sigma lambda minus k. And this means that the principal eigenvalue in this domain, I can read it as such. Oh, no. Of course. Well. Yeah, I should use it as a pen. Okay. So sigma lambda. Oh. Not only it's positive, but it's very large. And then you have maximum principal. And because of that, you see, so you say when you are here, you have v lambda minus u is bounded from below, so you can move it a little bit. This is compactness. And you can use it as a boundary condition on this part here. The other part of the boundary is you get it, you know it from to start with. So you can continue. You can go a little bit further than where you stopped at lambda star. You can continue. That's the essence of the moving plane method in the way we did it with Nirenberg, which does not assume any regularity of the domain. It's true in an open set, in a square and so on. And this is exactly what you have when you say stable compact. That's exactly the idea. And in fact, this proof I just gave, for instance, allows us, if you look at the old result I mentioned of Paul Rabinowitz, which used Hopf lemma, again, it was known in the domain of class C2. So our proof, just using the same proof and the same thing, allows you to say it's true in an open set. So in a square, it was not known in a square. KPP equation in a square, but the actual condition is unique. So with this, sorry to take more time, let me go back to the fantastic, next. No, this is not mine. Okay, so let me go to. Let me just say happy birthday, Vincenzo. Thank you for your attention.
Thank you very much for your marvelous, clear lecture. We understand a lot with the narrow domains for the maximum principle and so forth. So that's the time to questions, comments, remarks. There is some questions, some comments, some.
This is a marvelous talk.
Yes.
I have understood a lot of things. Thank you very much. It comes from the lectures I learned from Professor Brésil during the master degree in Paris. And this is a classical French tradition of mathematics.
Thank you. It's a great compliment.
Yes, it's
I know what you mean, and it's a great compliment.
Yes, it's a very. So that's a very interesting design of F. You said that you have a lot of nonlinearities, but the KPP is very interesting. Also in Minneapolis, there was Friedman, and many people work. So I learned a lot from them. But naturally, the sign of the nonlinearity is so important in elliptic problems, especially for uniqueness and so forth. So there are many papers also. James, what is first negative and then positive. And so you have also this type of, because there is a type of monotonicity with a KPP property.
Yeah, very good. It's a very right question. So indeed, so you are talking about questions of equations where f is f is like that. So f is like that, right? For instance, this is called bistable. So the Alenkane equation, for instance.
Yes.
So that's a very important type of nonlinearity. So the game is different there. Yes. The game is quite different. And let me point out why it's different. So if you are in all of Rn, so in all of Rn, for instance, the equation I drew before, it's easy to show, so there's no boundary condition. And it's easy to show that the unique solution, positive solution, is u equals 1. So when you, in Rn, so if I take KPP type, or even positive, provided the tangent here is non-zero, because when tangent is 0 is more complicated, but in f prime of 0 is positive. If you look at the equation minus Laplace u equals f of u, and u is non-zero, so u greater than or equal to 0, non-zero, suffices to give you this result, then this says u is equal to 1. There's only one solution, right? I'm sorry, I still have to improve this. Okay? But you see, if you go to the bistable case, then of course you have 1, but you have theta also as another solution, and then you have ground states. Yes. You have ground state solutions, right? When in this case we know that's a result I proved with Pierre Williams a long time ago, that in this case you have ground state and you can change the center. So there are ground state which are spherically symmetric with respect to the origin, but then you can move the origin around. So you have tons of solutions in this case. So it's very different.
Yes, you have to start, as far as I understand, from that point, where is important also the capital F is 0.
Right.
And
So,
then you
right.
start, yes.
So,
I have also some uniqueness.
right, absolutely. But if you look at this case, then the question is, can you restrict this looking at other domains? And by and large, this is open. What can you say about if you take? So we have some results for this in, for instance, in a half plane. In a half plane, we know this is a result I proved with Luis Caffarelli and with Nirenberg. In half plane, so in dimension 2, if I remember correctly, with u equal to 0, then the solution is indeed one-dimensional. So the solution is one-dimensional, and because one-dimensional is solution of the ODE, so then you see these solutions disappear as a constant, and the solution is one-dimensional, it's the solution of the ODE, and you can show that there's a unique such solution. So in other words, in this case, when you look at the bistable case, if you look at all of space, then there is many solutions. If you look at a half space, on the other hand, then there is, in dimension 2 at least, and I think we can prove it up to dimension 3, there is only one solution, basically, in the half space. So the question that arises there, can you prove this in more general domains? What are the classes of general? This is a fascinating question. Yeah. I believe that there are many interesting results lurking there, waiting for us to be gleaned from the tree, reaped from the tree. But so there are many young people here. Please go to the fields and glean those results.
Yes, very fascinating. As a Professor Magenes used to tell me in Pavia, that is always the uniqueness is the most charming problem we can have in mathematics. So thanks a lot. We thank for the marvelous talk of Professor Berestycki. The master professor. And we close with the closing address by Professor Cassani.
So thank you to all of you for participating to this Congress. We had 3 intensive days from the scientific point of view and also from the social point of view. And I want to add that another thing that Hari has in common with Aim is that when I hear a talk from you, everything looks simple, looks ideal, no? Looks thinking the same thing, no? Yes. Yes. Exactly. So, and you mentioned a few times Louis Nirenberg, a very close friend of us, and I'm sure most of the participants will miss him. And he used to refer to the mathematician community like a family. So I think that these days, this Congress is successful if we could succeed in make you feel this family. Did you feel that? Yes. So, big success. To thank you to all of you again. And as the scientific part ended with the Hari talk, say happy end, the social part will happy end with the lunch now. Okay?
Thanks to you, Daniel, to organize it.
Thank you very much.